Okie dokie, folks. So on this screencast, we're going to talk about the first derivative test. Now, that is not the first test you will come across that involves derivatives, but it is a test for increasing and decreasing behavior of functions that is based on the first derivative. So we're going to take a look at the first derivative today and what it can tell us about whether or not a function is increasing or decreasing. So I'm going to start us off with two of the three corollaries that yes, very good, that we took a look at last time we were together. They are corollaries of the mean value theorem. The one corollary says that if f prime is 0 at every point in some open interval ab, then f of x is a constant. This almost makes sense. If I draw some constant function, it appears that the derivative everywhere is 0. This corollary says that that works in the reverse also. If the derivative is 0, then the function has to be a constant. There's no other kind of function that does the job. Similarly, second corollary said that if I have two functions whose derivatives are the same, then those functions are the same except for a constant. And that almost makes sense, because if I have some ridiculous function that looks like this, and then I go ahead and clone the thing, those are two functions whose derivatives are the same, but they are different by vertical shift. So those things make sense to us if we think about it. And then I said we got to wait on the third corollary for this lesson, and so boom, here it is. Corollary 3 says, suppose that f of x is continuous on the closed interval ab and differentiable on the open interval ab. If f prime is positive on the open interval ab, then f is increasing, and if f prime is negative on the open interval ab, then f is decreasing. Quick word about the hypotheses. We want to be able to apply this corollary to functions that look like this, maybe semicircular in nature, where you have a vertical tangent here or a vertical tangent there. The function is continuous on the closed interval. It's just not differentiable at the endpoints necessarily. Maybe it is, maybe it isn't. This corollary doesn't care. So if f prime is positive, then f is increasing, and if f prime is negative, then f is decreasing. And this almost makes sense. If I could look at all the places where derivative is positive, and I can notice that f is increasing there, and I could look at all the places where the slope of the tangent line is negative, and I could recognize that f is decreasing in those places. And you could draw a whole bunch of functions that increase and decrease, and you'll see the same kind of connection. The thing is, we can prove this with the mean value theorem. We can actually prove this. It's a corollary of the mean value theorem. So what we're going to do is we're going to let x1 and x2 be some values in the open interval ab, and we're going to let x1 be to the left of x2. Here's what the mean value theorem says. The mean value theorem says that f of x2 minus f of x1 is f prime at some point c times x2 minus x1. And I'm going to hit the mental pause button on that just to reiterate. Mean value theorem says f of b minus f of a over b minus a, and we just kicked the over b minus a up to the other side in the equation where that quotient would be equal to f prime of c. So here's the significance. If x2 is bigger than x1, then this is some positive number. This is some positive number. Well, let's pretend that this is also some positive number, as it is over here. If f prime is positive, then a positive number times a positive number is a positive number. And what does that mean? That means that this is positive, which means that f of x2 has to be bigger than f of x1. In other words, f of x2 has to be bigger than f of x1. The function is in fact going up. And similarly, this is not going to be earth-shattering. If this is positive, what if f prime of c is negative, as it is on this side of our little picture here? Well, a negative number times a positive number is a negative number. What does that mean? It means that this is negative, and the only way for this to be negative is if f of x1 is greater than f of x2, which would mean the function is falling from left to right. So this is a nice quick sketch of a corollary of the mean value theorem, but it's a very powerful corollary because it tells us when functions are increasing and decreasing. So how does this pop up? Let's identify intervals of increase or decrease for f of x is x cubed minus 3x squared minus 24x plus 1. I want to be able to identify intervals of increase or decrease, and I don't want to have to use my magic knowledge box to do it. So we know from the first derivative test that if f prime is positive, f is increasing, and if f prime is negative, f is decreasing. So f prime, oh please tell me you knew how to do this, and then that factors, and I'll let you factor that in the privacy of your own home. Okay, just kidding. I'll factor that for you. X plus 2 and x minus 4. So what does that mean? That means that there are two critical values. There's a critical value at x equals negative 2 and a critical value at x equals 4. So if I were to generate a number line, which is a line with numbers on it, and I marked those two critical values on the number line, and then I looked at the behavior of f prime. Well, f prime is a so-called happy parabola. Happy parabolas start high, they go low for a little bit, and then they end high. F prime is positive all through here, negative all through here, positive all through there. Now, truth be told, if I don't know what parabolas look like, or if this is some other function that I don't know what to deal with, I could just sub in my favorite value between negative 2 and 4. Maybe you pick 0, and you sub that in, and you figure out that's negative 24. So if f prime of 0 is negative, they're all negative through that interval. Intermediate value theorem helps us establish that. I could pick my favorite value less than negative 2, sub it in here, and my favorite value bigger than 4, sub it in here, and figure out positive, negative, positive. So if f prime goes from positive to positive, f goes from increasing to decreasing to increasing. So I know that f is increasing on negative infinity to negative 2 and 4 to infinity. Why? Because f prime is positive on those intervals. And I know that f is decreasing on negative 2 to 4. Why? Because f prime is negative there. So I can very clearly establish with the first derivative test where f is increasing or decreasing. A quick OYO for you. Something to do quickly on your own. Identify intervals of increase and decrease for 3x to the fourth minus 8x cubed minus 18x squared plus 4. So hit the pause button, take derivative, set up a number line, establish intervals of increase and decrease. Okay? And so here's the way it looks. You figured out that g prime of x is 12x cubed minus 24x squared minus 36x. That's 12x times x squared minus 2x minus 3. That's 12x times x plus 1 times x minus 3. And so you've got your number line. And there are three critical values, 0, negative 1, and positive 3. And you know that this is a happy cubic. Happy cubics start high. Well, no, they end high. And then the signs go like this in between. We could check values to establish it, but I think this does a fairly good job. And so what do I know? I know that G goes from decreasing to increasing to decreasing to increasing. So G is increasing from negative 1 to 0 and 3 to infinity because G prime is positive. G is decreasing from negative infinity to negative 1, and from 0 to 3 because G prime is negative. Okay? Okay. So just a quick picture to catapult us forward in discussion. I got some function, looks like this. Oh, it's a standard picture in calc books at about this point. Some interval from A to B, and this place appears to be important, and this value appears to be important, and this one appears to be important, and this one appears to be important, and this one appears to be important. So let's take a look at the behavior of f prime in each of these little sub-intervals. So we can establish pretty quickly that between A and C1, what do you notice about f prime values? F prime is positive in there. And then what do we notice about f prime from C1 to C2? F prime is positive in there. And similarly, f prime is negative, f prime is negative, f prime is positive, and f prime is negative. Of some interest to us, there's a flat tan, there's a flat tan, there's a flat tan, there's a flat tan, there's a place where the derivative doesn't exist, so C5 is a critical point. Well, these, let's use magic pen. These are critical points where f prime does not change sign. F prime goes from positive to positive, f prime goes from negative to negative. So these are not places of interest, but this is a place of interest because that is a local maximum. And what happens at that local maximum? F prime changes sign. What happens at this local minimum? F prime changes sign. What happens at this local maximum? F prime changes sign. So it's not just that we have a flat tan, it's that f prime changes sign, and so we record that in something called the first derivative test. Suppose that C is a critical point of f, and that f is differentiable on an open interval a, b, except maybe at the critical points. I mean, maybe you got this thing going on. If f prime changes from positive to negative, there is a local max. If f prime changes from negative to positive, there is a local min. And if f prime does not change sign, then you have neither a max nor a min. This is key because this tells us exactly how to find maxes and mins for a function. And so let's do that. Let's actually, back to regular pen, let's actually find some extrema. Let's find all the extrema for f of x equals x to the fourth minus 4x cubed plus 4x squared. First derivative test says I want to know where f prime changes sign, so I need to know what f prime is. You had already figured that out before I even started talking, I'll bet. And this factors rather nicely into 4x times x minus 1 times x minus 2. So I've got three critical values. Three critical values. Got three critical values, three places where the derivative is 0 or undefined. This derivative is never undefined. Three places where f prime is 0. And I know that this is a happy cubic, so it starts low, ends up high a little bit, then goes low, then goes really high. If I wanted to substitute values on these little subintervals, I could, but I don't have to. I know how cubics behave. So what do I know? I know that f changes from decreasing to increasing to decreasing to increasing. So if I'm looking for local mins, I've got local mins at x equals 0 and x equals 2. Why? Because f prime changes from negative to positive there. And I have a local max at x equals 1. Why? Because f prime changes from positive to negative. F changes from increasing to decreasing. F prime changes from positive to negative. So if I think about what this function looks like, it's decreasing, increasing, decreasing, increasing. It looks roughly like this. And it turns out that f of 0 is 0, and f of 2 is 0, and f of 1 is 1. And so these local mins are both the absolute min. Well, the absolute minimum value is 0. It occurs at either of those places. And this max here is a local max, but it's not the absolute max because clearly the function increases beyond and increases beyond. Okay, so this is the first derivative test. It is very easy to apply because we just take the derivative, set up this kind of a number line, establish where f prime changes sign. Those are your mins and your maxes. Your 16 minutes are set. I look forward to seeing you tomorrow. Bye, everybody.